We're going to take a look at the two questions we had for homework last night on page 157, specifically, I guess, question number 2, which relates to the example 3.11, except that we're replacing the car tire mass with a mass of 15 kilograms. So let's go back to that example. Let's take a look at what our masses were. It says pail B was 8 kilograms, pail C was 6 kilograms. Let's label that. 8.0 kilograms, 6.0 kilograms. And I don't remember what the tire was, but we know that the tire is now 15 kilograms. We want to find the acceleration of this system. We know that we have a bunch of forces acting in this system. We know that we have gravity acting downwards on this guy. We know that we have gravity acting downwards on this guy, not quite as strongly though, because it's a 6 kilogram mass instead of 8. We know that we have gravity acting down on this guy, but we also have a normal force acting up, and they cancel each other out. So in all likelihood, I'm not even going to bother drawing those. We got two forces here that don't balance each other out. I'm going to call it FB and FC, or maybe you want to call it FGB and FGC. It doesn't really matter, as long as you recognize that it's gravity that's acting. Before I do that, though, before I analyze it, I'm going to actually pretend to straighten this out. Take the pail B, the first object, and kind of pull it up here. And then the second object, pail C, pull it up here. If I do that, it's going to look something like this. We're going to pretend we have an 8 kilogram object on a horizontal surface, a 15 kilogram tire on a horizontal surface, and a 6 kilogram object on a horizontal surface. If I do that, then the force of gravity acting on pail C will be to the right. And the force of gravity acting on pail B, which of course is going to be a little bit longer here, is going to be to the left. Why did I do that? What's the value in doing what I just did here? Nick? All right. Yeah, it looks like stuff we've done before, and there's value in making things look like things we've done before, right? Isaiah, what's the biggest reason why I do this, though? Yeah, it makes it apparent that things not necessarily cancel each other out because FB is bigger than FC, but that they're in opposite directions, right? That they've got to be negative and positive as opposed to both negative. If we look at the first diagram that we have, I mean, it's correct to go from there and not draw the second diagram. It's okay. The problem with that is that we often look at this and say, oh, the FB is negative because it's downward, and FC is negative because it's downward. And if I think I'm both negative, I'm going to get the wrong answer because even though they're both downward, they oppose each other. My signs right now aren't going to really represent left and right so much as forces that oppose each other. So when I redraw it, it makes it apparent, though, that one of them is positive and one of them is negative. All right, let's do this now. F net is equal to the sum of the forces. It's going to be FB plus FC, or whatever it is that you call them. F net is also equal to, what mass do I use here? 8, 15, 6, or a combination? The total, which is 29 kilograms, times the acceleration equals FB, which is 8.0 times 9.81, plus FC, which is 6.0 times 9.81. Is that right? No, what's wrong? What's wrong, Sebastian? Second number should be negative. This one? This one? Oh, okay. Oh, the other one. You want the other one to be negative. This one? Okay. You know, it doesn't matter. Something's got to be negative. Right? One of those forces has to be negative. Either FB, I just made FB negative. Okay, you were, I think, suggesting that we make this one negative. It doesn't really matter. As long as one of them is negative, one of them is positive. Right? If you make the other one negative, there's absolutely nothing wrong with that as long as you're consistent through the question and make the one that's opposite an opposite sign. Yeah, I tend to make the first one negative because it's acting to the left with the way that I have the diagram drawn. Some people like to make the other one negative because it's a smaller one. Some people like to make the bigger one the positive. Whatever works for you. As long as you recognize that one's negative and one's positive. All right, do the math on the right-hand side. 29A ends up being equal to 8 times 9.1, 6 times 9.1, negative 19.62. Do the math there. 19.62 divided by 29, I end up getting negative 0.68 meters per second squared. Now, what's the acceleration of the 8 kilogram object? Well, we'd say it's 0.68 downwards. The 15, it's 0.68 to the left. The 6 kilogram object, we'd say it's 0.68 upwards, right? In the end, you put this number, this answer for all of them, it's fine. Yeah, I'll take that answer for all of them because they're all accelerating with the same magnitude, right? It's like all those pallets of ice cream in the back of the truck. Yeah, they all accelerate at the same rate as the truck accelerates. All right. I would like you right now to take a look at the 5 questions that are given to you on the worksheet that's going out to you right now. These are all pulley type problems. Starts with one that's pretty straightforward. They get a little bit tougher after that, but I think that if you're able to do those questions we had for homework last night, I think you'll be able to handle the questions that are on this worksheet. All right, I want to take a look at question number 8. This one's a little bit different in the sense that we're solving for a different variable, but the setup of it is exactly the same as the other questions that we've done. So let's do that now. Let's straighten it out. Let's pretend in question number 8 we've got a 3 kilogram object right here, but we've got a 5 kilogram object right here, and a 12 kilogram object right here. We know that there's going to be a force of gravity. I'm going to call it Fg1 to the left as a result of the 5 kilogram object. We're going to have a force of gravity to the right. I'm going to call it Fg12. Maybe I just want to call it F1. Sorry. You know what? Actually, let's call it F12 and F5. Let's do that. Doesn't really matter as long as I recognize what it is that's causing those forces. Now, there's also a force of friction. Do I know which way friction acts? I do, although it doesn't really matter if I recognize that in this question because I'm going to solve for it. And when I solve for it, it'll tell me which direction it is. But you know what? If you can add it in right now, so much the better. Nick, which way does it act? Yeah, it's going to act to the left. And it's going to be on the 3 kilogram object, right? We don't know what its value is. All right, so let's set this up. Let's say F net is equal to the sum of the forces. It's F5 plus FF plus F12, or whatever you called it. F net is equal to the total mass, which is going to be 20 kilograms. The acceleration we're given is 2.0 meters per second squared. F5, we're going to make 5 times negative 9.81 plus FF plus, this is going to be 12 times 9.81. Positive. Now be careful here, okay? Be really careful with this. I know there's at least a couple people that made this mistake in this question here. Some people like to change around the negatives and positives, and that's okay. Like if you make this one negative because it's a bigger value, because it's acting down more, there's absolutely nothing wrong with that. But if you're going to do that, you got to recognize that this acceleration has to be negative as well. Right? We give you the magnitude there is 2.0 meters per second squared. It's accelerating to the right, we'll say. Right? This one's going up, this one's going to the right, this one's going down. Okay, it's accelerating this way. If it's accelerating this way, then that acceleration has to be the same sign as that force. If that force is positive, the acceleration is positive. If that force is negative, then the acceleration is negative. Okay, I'm going to stick with A as being positive. Therefore, F12 is going to be positive, and F5 is going to be negative. 20 times 2 is 40. 5 times 9.81 is negative 49.05. 12 times 9.81, I'm not sure what that is. 117.72. Okay, let's add those together. On the right side, what do we get about, what is it? 68.67. It's positive. Take it to the other side by subtracting, and I think we end up getting negative 28 or negative 29 newtons, I guess it would be. Good there? Right. If you did it the other way and made this one negative and this one positive, then you would have gotten a value of positive 29 newtons. Right? Bottom line is, we know from my diagram that FF should be the same sign as F5, because they're both acting to the left, both opposing the motion. One new example. This is on page 179 of your textbook here. So it's a little bit different. We're on an incline. For the first time, we're going to find that the normal force and gravity do not cancel each other out here. Remember, I've been telling you all along, hey, look, gravity and normal force is the same value until I tell you different. I'm telling you different now. Let's draw the free body diagram for this and see what happens. Okay, we know that we have a force of friction acting up the hill, right? We know it's going to be act up the hill because the motion of the object, if I just let it go, it's going to be down the hill. It's going to slide down. Therefore, friction has to oppose that. So I'm going to say FF, 3.9 newtons, up the hill. But now let's focus on gravity and normal force here. Gravity is going to act downwards. And that force of gravity is m times g. Agree? Straight down toward the center of the earth. Regardless of what incline the hill is on, gravity is going to act straight down. The normal force, on the other hand, is not going to act straight up. It's not going to directly oppose gravity, but rather it's going to act at 90 degrees to the surface, right? Now, I don't want to draw it there. Lots of you are going to say it seems convenient to draw it there, less clutter to draw it there. You know what? It is. It is less clutter to draw it there. But I still want to draw it down here where it's a little bit more cluttered. You'll see why in just a second. So let's label that Fn. We've got Fg labeled as m times g. We've got Fn labeled. You notice something when you see both of these drawn? Notice when I draw it this way, they're drawn front to back. I can add those vectors together, right? When I have two vectors drawn front to back or head to tail, like I have them drawn right there, then I can add them together. The sum of those vectors ends up being this one right here, right? It's drawn from start to finish. You guys remember the rules of vector addition back in Unit 1? I'm going to call this F parallel. Why do you think I'm going to call it F parallel? F parallel looks like F11, but those are two parallel lines. Yep. Yeah, because it's parallel to the incline. I'm going to redraw F parallel up here. It's not two of them. It's not two values of F parallel. It's the same thing. I'm just redrawing it up here. It's F parallel that drives this object down the hill. I should have asked you at the beginning of this, what pulls it down the hill? And I would bet that the answer that you guys would have given me would have been gravity. Gravity pulls it down, but gravity doesn't pull it down and left. It doesn't move straight down, so there's got to be something other than gravity contributing to the motion of this thing, right? If I look at gravity pulling it down, and the normal force, ironically, the normal force that pushes it up is helping it go down the hill. Because there's a left component of the normal force, right? A horizontal component of the normal force. The downward component of gravity and the leftward component of the normal force end up taking it down and to the left, down the hill. Look, this F parallel, that's the force I want here. Because F parallel acts along the plane of the motion. I want FF, which was easy, and I want F parallel, which is the combined normal force and gravity. Now, how do I find the value of F parallel? Well, it's not quite as bad as you might think. Firstly, recognize that F parallel always has to be drawn parallel to the surface. That's why I called it F parallel. And of course, if the normal force is drawn 90 degrees to the surface, the angle between F parallel and Fn will always be 90 degrees every time. Now, also recognize that if this is 15 and this is 90, this is going to actually be 75. 15 plus 75 plus 90 gives me 180. And if that's 75, then this angle right here is going to be 15 degrees. 90 minus 75 gives me 15. That will always be the same angle as this one as well. So if you're given this angle of the hill here, 15 degrees, 30 degrees, whatever, then the angle that's inside the triangle will be that same value, 15, 30, whatever. Yep. We're not going to use the sine law, but we are going to use some trigonometry here. Yeah, no, I mean, yes, because in the end, like that, whenever you have those sides, you can do that, right? But I think it's simpler when you have a 90-degree angle to use just sine or cosine, right? Okay, we would tend to do that probably when we don't have a 90-degree angle, which we never use that. We never use the sine law or cosine law in physics. We never do. I personally, I think it's easier to go get the 90-degree angle I think it makes more physics sense to do that. But in this case, we already have the 90-degree angle. So to me, in this case, it's a no-brainer. In this case, to find F parallel, I'm going to use sine 15 degrees equals opposite over hypotenuse. Hypotenuse being the force of gravity. So F parallel, which I'm going to look for here, is equal to mg sine 15 degrees, which is what, 3.5 times 9.81 times sine 15 degrees. What do you get when you multiply those together? 8.8. What's the unrounded number there, Isaiah? 8.799. All right, so let's label this now. Now I got both forces that are parallel to the surface. Notice my force of friction, though, looks to be drawn too big, right? It's not a huge deal, but I'm just going to redraw that. Make it 3.9 newtons. Okay, now what do? You know this. Yep. Good. F parallel plus FF. Now, explain this one to me. Why do I not include Fn and Fg when I do the net forces equal to the sum of the forces? Remember what I said before? If they cancel, then you don't have to include it, right? They don't cancel here. Fn and Fg do not cancel here. Yeah, Fn is up at an angle, Fg is down, straight down. Jackson, why do I not include them when I'm writing Fn is equal to the sum of the forces if they don't cancel? Yes, exactly. I am including them. I am including them. F parallel is Fn and Mg. You got that? Like, I do have to include them, but I am, by virtue of the fact that I've combined Fn and Fg to get F parallel and then solve for its value. The net force is equal to 3.5 times the acceleration. F parallel is negative 8.799 newtons, and force of friction is 3.9 newtons. Look, it's the same as any other question now, right? The trick in this one was getting the value of F parallel. What do we get? 3.9 take away 8.799, divide that by 3.5, and we had to get a value for the acceleration of negative 1.4 meters per second squared. So what makes this question different than the other questions that we've done so far? This, getting the value of F parallel. Your homework for tonight, for the weekend, is to take a look at these two questions on page 179. Please, when you're doing those questions, use this as a guide. And remember these little things, right? F parallel, a lot of people like to draw this like this. This is not F parallel. F parallel must be parallel. That's what we call it, F parallel. And that angle between Fn and F parallel is always going to be 90 degrees. You get those little things like that, all right, and it tends to go pretty well for you. Let's finish up those two questions for homework on the weekend, and we'll take a look at them on Monday.